1.5, the limit of a function. So when we talked about the tangent problem, the concept of limit arose. So we're going to look at another example of a function f of x equals x squared minus x plus 2. And we're going to investigate the behavior of f. The behavior of f. In other words, we're going to look at the y values when x is near 2, but not equal to 2. But not equal to 2. So in the neighborhood of 2. So let's make a table with values for x and f of x. So we're going to pick values of x near 2. Let's start with values less than 2, 1.995. And if we substitute it in the function, we'll get 3.985025. If we have x equals 1.999, even closer to 2, the y value is 3.997001. And now from the right, the value is greater than 2, 2.005. The y value is 4.015025. And one more, 2.001, very close to 2, but from the right. And the y value is 4.003001. I can always also show the graph. And so the graph is a parabola. And here is 2. Let's say this is 2. So as we're approaching 2 from the right or from the left, what's happening to the y value? Okay, if you plug in 2 exactly, you're going to see that it's 4. So if x is 2, y is 4. But we don't care what's happening at 2. We want to investigate behavior of f in the neighborhood of 2. So as we can see from that table, using intuition, as x approaches 2, f of x is approaching 4, of course. We can write this down using the notation, the new notation, the limit of our function x squared minus x plus 2. When x is approaching 2, and that means x is approaching 2 from the right and from the left, and this limit is 4. So a formal definition for a limit, we're going to write down, in general, let f of x is defined, f of x is defined when x is near a. When x is near a. In our previous example, our function was defined everywhere, including at the point 2. So we want f to be defined in the neighborhood of a. And what that means is defined in an interval containing a except at a itself. Then we write that the limit of f of x when x is approaching a is L. If we can make the values of f of x, so we write this down, if we can make the values of f of x arbitrarily close to L, by restricting x to be sufficiently close to a. On either side of a, but not equal to a. So x doesn't have to equal to a. We don't care if it does. That's not important. So we write that f of x is approaching L as x is approaching a. So this is equivalent to writing that the limit that is equivalent of writing that the limit of f of x when x is approaching a is L. A quick note, in finding the limit of f of x, we never consider x equals 0. So in finding the limit of f of x when x is approaching a, we never consider the possibility of x equals a. F of x need not to be defined when x equals a. The only thing needed is that f is defined near a, in the neighborhood of a. So I'm going to show some pictures here of several situations. I have this very nice graph. It's continuous everywhere, and here's A, and here is L. Obviously here, f of x is defined at A. Okay, so it's continuous at A, and f of A is equal to L. The limit of f of x when x approaches a is L. No questions about it. Now let's change this. The same function, f of x, but when x equals a, we're going to have a hole here. That graph has a hole. In other words, it's not defined. So at that point, but we're going to add a filled-in circle here. So we're going to say f of x is defined at a, but f of a is not equal to L. So where is L? L is right here. So in this case, we redefine the function at a. The limit of f when x approaching a is still L. We have a hole, which we had redefined. So the limit is still L. And the third case, we have the same function f of x. We have a hole when x is a, and we're not gonna define it. We're just gonna say f of x is not defined at a. It's not defined at a. But in this case, you can still see that the limit when x approaches a is still L. So it didn't matter if it was defined or not defined. So a few examples. Investigate the limit of sine of x over x when x is approaching 0. I'll show you the graph. So the graph looks like this, but at x equals 0, as you can see, it's not defined, right? Because we can divide by 0. Well, this limit is 1, okay? And that actually will become one of our formulas, the very important. We'll be able to prove it later on, but the limit of sine of x over x, even though it seems undefined, sine of 0 is 0, so it looks like indeterminate, 0 over 0, but that limit is 1. It's really easy to prove with L'Hopital rule, which we can study in Calc 2. Okay, another example. Investigate the limit of sine of pi over x when x approaches 0. So let's look at our function. F of x equals sine of pi over x. And this function is undefined when x equals 0. So we can pick other points. 1. 1 is the neighborhood of 0. So what's f of 1? Substitute x with 1. You have sine of pi, which is 0. Then we're going to see 1/3. What's f of 1/3? That's close to 0. That's sine of pi over 1/3, which is sine of 3 pi, which is 0 again. And we can keep going. 1/4, 1/2, really close. How about 1/10? That's sine of pi over 1/10. Sine of 10 pi is still 0. So we're getting close to 0 by picking points 1, 1/3, 1/2, 1/10, close to 0, and we're getting 0. So we may be tempted to say, it may be tempting to say that the limit of our function when x approaches 0 is 0, but that will be incorrect. And we can disprove this with picking another point, for example, 2/5. If x is 2/5, which is close to 0, what is f of 2/5? That is sine of pi over 2/5, which is sine of 5 pi over 2, which is sine of pi over 2, which is 1. So it's not 0. So it didn't work. Our assumption was wrong, and I can show this with the graph. So the graph goes through -1 and 1, and for values around 0, it is 0, but not always, because it oscillates. Okay, so it goes back and forth between 1, -1, and at some points it is 0. All right, let's talk about one-sided limits. One-sided limits. A function, we'll call it h. It's a piecewise function equal to 0 if t is negative, and equal to 1 if t is greater or equal than 0. So this is a piecewise function. Let's graph it. If t is positive or 0, y value is 1. So we have this horizontal line going that direction, and if t is negative, then it's 0. I'm going to use a different color for the function. So we have this to the right, and we have this to the left with a hole here. Oh, actually, I need to draw it over here. It's 0, not -1. So this is our function, which we call h of t. And as you can see, something is happening at 0. What's happening is that the line is broken down. Okay, so as t approaches 0 from the left, the function, the y value, is approaching 0 from the left, right? And as t is approaching 0 from the right, our function is approaching 1. As you can see, we have two different limits. The right-hand limit is 1 and the left-hand limit is 0. So they're different. We say that the limit of our function when t approaches 0 does not exist. Okay, so it has a left-hand and a right-hand limit, but the limit at 0 doesn't exist because both right-hand and left-hand limit are different. Okay, so let's look and write down this fact that's very important that we just observed from this picture. We say that the limit of f of x when x approaches a is L if and only if the limit of f of x when x approaches a from the left is L, and the limit of f of x when x approaches a from the right is also L. So in other words, we can use this fact to show limits or to prove the limit exists if the right hand and the left hand limit are the same. So quick example. of a function that's piecewise and starts here, and it has, it's not defined at 2, right here, has a big jump, like that. And at 5, it's redefined here, so we're gonna add a point here. So this is our function g of x. This is 1, 2, that's more like 4 here, but I'll leave it as 5. Okay, and that point here is 3. So let's investigate the limits here at several points. What is the limit of a function when x approaches 2 from the left? So from the left, that means pick 1.9, 1.99. The y value is approaching 3. Okay, what is the limit of this function when x is approaching 2 from the right? So from the right, like 2.1, it seems like it's different. It's 1. So these two are different. We say that the limit of g of x when x is approaching 2 does not exist. We have a big jump. Okay. Now the limit of our function when x is approaching 5 from the left. Okay, I'll add a point here, that's 2. And the limit of g when x is approaching 5 from the right, it's also 2. Okay, so it didn't matter that we had a hole here, that we defined it. Because of these two facts, we say that the limit of g of x when x is approaching 5 is also 2. Now let's add something else and find out what is g of 5. So there's a limit when x is approaching 5, but g of 5 is not 2, it is 1, and that's all right. Infinite limits. Infinite limits. So example, find the limit of 1 over x squared when x is approaching 0, if it exists. So we can look at the graph. It's a rational function. Or you can make a table. We can also make a table. And we can say if x is 1, f of x is 1. If it's -1, it's also 1. This is even functional. We can give positive and negative together, plus minus 1/2, and you get 4. And let's give some big numbers. Small numbers, plus minus 0.001, and that is 1 million. So it gets really, really large. So the closer you are to 0, the larger the numbers for f of x you have. So we can say that as x is approaching 0 from the right and from the left, x squared is approaching 0 as well. But 1 over x squared is very large, so it's approaching positive infinity. We write this as the limit of 1 over x squared when x is approaching 0 is equal to infinity. So this doesn't mean that we regard infinity as a number, nor that the limit exists, but it exists in a particular way, because both the left hand and the right hand limit go to positive infinity. Then that's how we write the limit, and we call this infinite limit. All right. So connection that we see here, we had an infinite limit at 0, and what do we have at 0? We have a vertical line. So there's a connection between a vertical line and infinite limit. We say that the vertical line x equals a is vertical asymptote of the curve y equals f of x if at least one of the following is true. If at least one of the following is true. And what I'm going to write down is several limits, 6 of them. So the limit of f of x when x is approaching a is infinity, or the limit of f of x when x is approaching a from the left is infinity, or the limit of f when x is approaches a from the right is infinity, or all that we're going to write down, but instead of infinity we're going to put negative infinity. And lastly, x is approaching from the left or from the right. Okay, so you have 6 possibilities for a vertical asymptote. So let's look at this picture. I have some function here, f of x, and it has a vertical asymptote at a. Okay, so this is vertical asymptote. The equation is x equals a. Which one of the previous 6 limits is true here? So this is not touching actually, right? Continuous. So the limit of f of x when x is approaching a from where? In this case, we're approaching from the left, and that limit, it goes down, so it's negative infinity. So we see we have one-handed limit, a vertical asymptote. Okay, another example. Find the limit. Find the limit. So limit of 2x over x minus 3. X is approaching 3 from the right. So we're going to find this limit, and then we're going to find same limit that x is approaching 3 from the left. You can make a table, or you can look at the graph. So the graph of this rational function is not defined at 3. So here's 3, right? Because if x equals 3, denominator is 0. So we're going to have this vertical asymptote. And if x equals 0, y is 0. So it goes through the origin. Just roughly sketching this. And on this side, something like that. So this point is 3. You can either make a table or look at the graph. So what's happening if we're approaching 3 from the right? Values like 3.1, 3.01. What's happening with the y value? It's really, really big. So that is positive infinity. Now what's happening if you approach 3 from the left? You go down to negative infinity. So these two limits are different. What can you say about the limit when x approaches 3? That doesn't exist. And that concludes the lecture for 1.5.